Hey everyone, today we're learning the fundamental theorem of calculus part 1. FTC part 1 is all about the integral function, or a sum function that is defined as the integral from a to x of a second function. We can look at it geometrically on this side here. You can see that it just models the area under the curve of the function f from a to x. And you can imagine as x increases, then this area will grow, and so g of x will increase. It's pretty simple, but FTC just models what the derivative of this function looks like. Basically, if f is continuous, or if what you're taking the integral of is continuous, then we know that g is differentiable and g prime is equal to the derivative of integral from a to x of f of t dt, which is just going to be equal to f of x. So the main idea is, if you have an integral function, and if f is continuous, then g is differentiable, and the derivative of the integral from a to x of f of t is just f of x. Replace all the t's with x's, and you're basically done. Now let's look at some examples. This first one we have here is an integral function from 0 to x of e to the minus t squared dt. Well, we know minus e to the minus t squared is continuous, so we know that g prime, or g prime of x, will simply just be equal to whatever f of x is, or f of x here is e to the minus t squared. We just replace all the t's with x, and we're done. So this will be just e to the minus x squared. That's the easiest example. Let's move on to the next one. Here we have a different one, but instead of having x, we have x cubed. Basically, all we're trying to test here is that when we take g prime of x, you replace all of your t's with whatever you have here, end up with cosine of x cubed, and we just need to remember the chain rule. Since this isn't exactly just x, this is x cubed, we take the derivative of this and multiply at the end. So this would be 3x squared. And that would be the solution for our example 2. Remember, chain rule applies. Chain rule applies still with FTC. And now continuing on, what happens if we have a function of f in both the bottom bound and the top bound? Well, if you kind of think of it this way, we can take this as, the integral from 0 to e to the x of blah, 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 plus the integral from x squared plus 3x plus 1, to 0 of blah, 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 right? You can split it up this way. And then if you were to just take this, turn that into negative sign, what's on the bottom bound goes to the top, and what's on the top bound goes to the bottom. And so you can just switch them like that. So what you just end up with is you just use FTC normally for the first one, and then you just subtract what you get with FTC normally for the second one. So let's do the first one. So we know that g prime is going to be equal to sine of e to the x times the derivative of e to the x, which is e to the x, subtracted by, remember how we derived this? The same thing, except just plug the bottom one in. Minus sine of x squared plus 3x plus 1 times the derivative of this bottom one, which is just 2x plus 3. And then we're done. In all, FTC 1, Fundamental Theorem of Calculus 1, is easy if you just remember these 3 things. The first thing is, if you have an integral function, the derivative of it, if f is continuous, is just take all the t's in f and just replace them with x's. It's that easy. Second of all, the chain rule applies. If you have, instead of x, h of x as a bound of integration, you'll do the exact same thing. Replace all the t's with h of x's, and then just multiply by the derivative of h afterwards. And last of all, if you end up having 2 bounds that are both functions, you can simply split it into 2 and do it that way. And you end up with that g prime of x is equal to f of h of x times the derivative of h minus f of p of x times the derivative of p. Good luck in all your courses, and I'll catch you next time.